Okay, for this next problem, number 5, we want to show that the span of the vectors 1, -1, 2, 2 explicitly spans two-dimensional space. So we have to show for any vector AB, there's a solution to the vector equation C1, 1, -1, plus C2, 2, 2 has a solution. Okay, has a unique solution. Okay, we don't want to show that it has infinitely many solutions. We want to show that it has a unique solution. So that means what we want to get is a formula for C1, C2 in terms of A and B. All right, to do this, we use our usual trick of solving the augmented matrix for A and B. Okay, so let's see what happens. If we add row 1 to row 2, we obtain one stays fixed, and we add row 1 to row 2, we get 0, 4, A plus B. Okay? Now we're stuck with fractions at this point. We'll divide row 2 by 4. Okay, that gives us 1 here. And then we'll subtract row 2 from row 1. Let's see what that yields. Okay, so if we have, we'll subtract 2 row 2s from row 1. So we have 1, 0 and 0, 1 over here. And let's see, we have A plus B over 4. That's A over 4 plus B over 4, right? So when we subtract 2 of those, we have A minus 2/4. So that's 1/2 A minus 2 B over 4. So that's 1/2 B over 4. Okay, going back to the land of equations, where we never were, we obtain C1 is equal to 1/2 A minus 1/2 B, okay, and then C2 is equal to A over 4 plus B over 4. Okay. All right, so let's see what happens. That's a formula for how to obtain C1 and C2 to get to any target vector. I didn't pick a target vector, but let me pick a target vector. How about we pick a target vector so that we reduce our dependence on fractions? How about A is a multiple of 4 and B is a multiple of 4? So if A is a multiple of 4, we can let A be equal to 4, and we can let B be equal to 8. Okay, so C1 then would be equal to 1/2 of 4, which is 2, minus 1/2 of B, which is 4, and 2 minus 4 would be equal to -2. So C1 is equal to -2. C2, on the other hand, is going to be A over 4, which is 1, plus B over 4, which is 2, and that gives us a 3. So that tells us that -2 of vector 1, which is this vector here, V1, I'll call that V1, and I'll call this V2. So -2 V1s plus 3 V2s should take us to our target vector. And let's see if that happens. So if we have -2 times the vector 1, -1, all right, plus 3 vector times vector 2, which is 2, 2. And let's see if that carries us to our target vector. -2 plus 6 is indeed equal to 4, and 2 plus 6 is indeed equal to 8. All right, so I just picked an arbitrary vector, albeit an arbitrary vector such that A and B are both multiples of 4, to reduce our dependence on fractions. And we see that the vectors 1, -1, 2, 2 carry us to our target vector. And that's all there is to it. So here's the formula for C1, and here's the formula for C2. So you can see that we have unique solutions for C1 and C2. And that shows us that these two vectors, 1, -1, and vector V2, 2, 2, span two-dimensional space explicitly. Good. Okay, number 7, we want to find the null space of this matrix, the same matrix that we found the column space before. Well, to do that, what we do is we look for vectors x, y, and z such that when we multiply the matrix into x, y, and z, we obtain a result of 0, 0, 0. Okay, I'll draw a depiction of this, right? So suppose this is R3 and this is R3 because you see this matrix that we have maps R3 to R3. In other words, if you take an input of a three-dimensional vector, you get an output of a three-dimensional vector. What we're looking for is the null space, and that's the set of all vectors in R3, right? The domain, I'll call this domain, this range, right? Such that those vectors get mapped to 0 in the range. All right, so let's do what we usually do, and we'll write down the augmented matrix, okay? 1, 1, negative 1. And this is going to be a lot easier to reduce because we don't have to keep track of much on the right-hand side. Everything's 0 on the right-hand side of this matrix. So let's add 2 row 1s to row 2, and we'll have row 1 be unchanged. Okay, that gives me 0. 2 of these added to that, it gives me a 5. 2 zeros added to 5 is 5, and 2 zeros added to 0 is 0. Also, let's take row 3 and subtract off row 1. So 1 minus 1 is 0. 1 minus 2 is negative 1. Negative 1 minus 0 is also negative 1. And once again, 0 minus 0 is 0. All right. So now we'll eliminate we can divide row 2 by 5, right? Divide row 2 by 5. And then we'll add that row to the bottom, which gives me zeros in the bottom row. Okay, so now we have zeros here. And one more step. Let's take row 1 minus 2 row 2s. So this 2 is going to disappear. This is going to put it in reduced row echelon form. And then 0 minus 2 1s is negative 2. Okay, so when we evaluate the null space, let's go back to the land of equations, where we never were, because we wrote our linear system initially in matrix form. So back in the land of equations, we have x minus 2z equals 0, and y plus z equals 0. All right? Notice that there's nothing said about z, so z is a free variable. So it looks like we're going to get a one-dimensional null space because with one free variable, we'll assign that free variable z to be equal to t. Thus, y is equal to negative t, and x is equal to 2t. Okay? Right? And this solution, if we write down the solution, what do we have? S for the null, and I'll write it as the null space. Okay? Thus, the null space of this matrix A is equal to the set of all vectors such that the components are 2t, negative t, and t, such that t is any real number. Okay? There we go. T is any real number. Now, of course, if we choose t to be equal to 0, that's not very interesting because x, y, and z will all be equal to 0. And we know that 0 is in the null space of A because if we take the 0 vector and hit it with this 3 by 3 matrix, we get the 0 vector in the range. All right? But let's take t to be something non-trivial, like 1. All right? If t is equal to 1, we obtain the vector, let's see, what vector do we obtain? If we let t be equal to 1, we obtain the vector 2, negative 1, 1. Now let's see if that vector is in the null space, okay? So I'll substitute this vector in for x, y, z, and we hope that we get zeros. So we have 2, negative 1, 1. And let's do the dot product thing, as I fondly say. So if we do the dot product thing, we have 2 minus 2 plus 0 is indeed equal to 0, right? Then we have negative 4 minus 1, that's negative 5, plus 5 is equal to 0. And then finally we have, let's see, 1 times 2 is 2, minus 1 is 1, minus another 1 is 0. You see, so this is a non-trivial vector. The vector, I don't know if I can squeeze it in here, 2, negative 1, 1 is a vector that gets sent to the 0 vector in R3. And we can get infinitely many of them. Of course, it's one-dimensional because we have only one free variable. Nevertheless, we can get infinitely many vectors that get sent to the zero vector. Now, I just want to make a comment about this. You see how the null space is one-dimensional, right? It's, I drew it as a circle, but it's really one-dimensional. It's a line in three-dimensional space. Whereas when we computed the column space of this matrix before, we found that to be two-dimensional. Well, this is an illustration of the fundamental theorem of linear algebra, which says that the dimension of the null space plus the dimension of the column space of a matrix is equal to the domain space, which is 3. And we see 1 plus 2 equals 3. Awesome. Okay, so for the next question, we want to find the column space of A. So what we do in order to determine that is we write the linear system C1 times the vector 1, negative 2, 1, plus C2 times the vector 2, 1, 1, plus C3 times the vector 0, 5, 1. And we see if we can reach any vector A, B, C. We won't be able to because these vectors are not linearly independent and don't span three-dimensional space. So this is going to be conditioned on one of the variables A, B, and C. We're going to work it out so we have a condition on C. All right, so let's do what we usually do and form the augmented matrix. Doing so, we have 1, negative 2, 1, 2, 1, 1, and 0, 5, 1 equals A, B, and C. And let's row reduce this. Okay, in order to do so, we'll add 2 row 1s to row 2. So 1, 2, 0, A. All right, and then we have we have the 0 here, a 5 here, a 5 here, and 2 A's added to B is 2A plus B. Now we'll take row 3 minus row 1. That gives me a 0, a negative 1, and a negative 1. This is a negative 1 here. All right, sorry about that. And a negative 1. And so we have C minus A. Okay, let's write that as negative A plus C. All right, to eliminate the leading number in the second row, we'll use negative 1 and add 5 row 3s to row 2. All right, doing so, what do we have? We'll get a 0 here, we'll get a 0 here, and then we'll get 5 negative A's added to 2A. That's negative 3A, right? Negative 3A plus B, and then plus 5 C's. Plus 5 C's, okay? There we go. And notice that the second row is entirely consists of zeros. Let's interchange rows 2 and 3. All right, I'll do that up here. This is step 2, this is step 3. Step 4, we'll interchange, and we have 1, 2, 0, A up here. 0, I'll multiply the third row by negative 1. So we have 0, 1, 1, and that gives me A minus C. And the third row will be 0, 0, 0, negative 3A plus B plus 5C. Okay, so this tells us that there's going to be a condition on one of the variables. Let's let the condition be on C. In other words, let's let negative 3A plus B plus 5C equals 0. It has to because with coefficients C1, C2, C3 equals 0, 0, 0, there's no way to get to an arbitrary negative 3A plus B plus 5C. Indeed, if A was 1 and B was 1 and C was 1, what would we have? 5 plus 1 is 6, minus 3 is 3. So there'd be no way to get to the number 3 in the third row with 0 coefficients. So let's solve for C. So we have 5C is equal to 3A plus B. Therefore, dividing by 5, we find that C is equal to 3A plus B over 5. That's going to be our condition. So let's pick a target vector with that condition, okay? So if we do that, how about we let A be equal to 7 and B be equal to 1, because that's going to give me a multiple of 5, because 21, this is a minus B, okay? Sorry about that. So if A is equal to 7 A is 7, B is equal to 1, and that would mean that C would have to be equal to 21 minus 1, which is 20. 20 over 5 is 4, and C would have to be equal to 4. So that means we should be able to get, with these three transport vectors, to 7, 1, 4. And to demonstrate that, let's put a 7, 1, 4 over here, and again, solve the linear system. I'll try to do so quickly and accurately. 1, negative 2, 1, 2, 1, 1, and 0, 5, negative 1 equals 7, 1, 4. Okay? All right, good. Let's row reduce again. Here we go again, right? Deja vu all over again. So we'll add 2 row 1s to row 2. Good. So that gives me 1, 2, 0, a 7 up here. And then we add 2 row 1s. On the left-hand side, we get 0, 5, 5. 2 7s plus 1 is 15. Nice, because we can divide by 5. And then row 3 minus row 1 gives us a 0. It gives us a negative 1, a negative 1. And 4 minus 7 is negative 3. Let's multiply row 3 by negative 1, get rid of the negatives. So we have 1, 1, 3 in row 3. Now how about row 2 minus 5 row 3s? Well, that's going to wipe out row 2 entirely, right? Because we're going to have 5 minus 5 1s, which is 0. 5 minus 5 1s is 0. And 15 minus 5 3s is 0. Okay? If we go to the next step and interchange rows 2 and 3, we have 1, 2, 0, 7. Okay? And then we have 0, 1, 1, 3, and 0, 0, 0, 0. That's a good thing, right? Because with coefficient C1, C2, C3 equals 0, we can only hope to obtain a 0 as the third component. All right, so let's proceed. Okay, I want to keep this linear system here in vector form so that we can check our answers. One last step. How about we take 2 row 2s away from row 1? So 1 minus 2 zeros is still a 1. 2 minus 2 1s is a 0. And 0 minus 2 1s is a negative 2. And 7 minus 2 3s is a 1. Okay? All right, good. We're ready to return to the land of equations. So what do we have? We have C1 minus 2C3 is equal to 1. And therefore, for the second row, we have C2 plus C3 is equal to 3. Notice that there's no condition on C3, which means that C3 is free. We'll call it T. All right? So if C3 is equal to 3, T rather, then C2 is going to be equal to T 3 minus T, right? And C1 is going to be equal to 1 plus 2T. All right, so why don't we pick T equals 0? If we pick T equals 0, then C3 equals 0, C2 equals 3, and C1 equals 1. Now, if C1 is equal to 1, let's put the 1 over here, and C2 is equal to 3, put the 3 over here, and a 0 over here, can we get to 7, 1, 4? Let's hope so. So how about this? 1, 1 plus 3 times 2 is 6 equals 7. Yay. How about negative 2 plus 3 is 1? Good. And 1 plus 3 is equal to 4. So 7, 1, 4, as predicted, is going to be in the column space of the matrix A. That means these three vectors, v1, v2, v3, I'll label them, v1, v2, v3, will carry us to 7, 1, 4. But there are conditions, right? The condition was, I'll reiterate that C is going to be equal to 3a minus b over 5. So any vector, any value of C that satisfies this, A and B can be anything we want them to be, but C has to be equal to this number, then we can get there, right? Another choice would be, let's see, how can we make this a multiple of 5? If A is equal to 8, 9, no. Yeah, I guess if A is equal to 9, then we have 27, and B is equal to 2, right? We have 27 minus 2 over 5, then c can be equal to 5, right? And then we would get 3 integers, and you can try that out for yourself. Put a 9 here, a 2 here, and a 5 there, and that 2 will be in the column space. Now observe that the column space is inherently two-dimensional, right? Because we have only 2 degrees of freedom. A is free and B is free, but C is not free. C is determined by A and B, okay? Keep that in mind, that the dimension of the column space is two-dimensional. We could actually, provide 2 vectors that span. Indeed, if I just chose V1 and V2, they would span the column space. V3 is unnecessary. If we took negative 2 V1s plus V2, I think we would get there, right? Yes, we could write the third vector as negative 2 V1s plus V2, and we get the third vector, meaning that the third vector is unnecessary. So like I said, inherently two-dimensional. Good. Now, problem number 9 is false, okay? Okay. Problem number 9 says the following. True or false, let V be a vector space, then any 3 linearly independent vectors is a basis of V. Well, it's a little bit of a trick question, because you see the dimension of the space could be 10, right? And certainly 3 linearly independent vectors are not going to span R10, right? So 3 linearly independent vectors will span R3, but they won't span R10. Okay, so the answer to number 9 is false. So number 10, we have 2 bases for two-dimensional space. And I'll tell you in advance that they're bases. You can easily see that because the vectors I'm about to write are linearly independent. So beta 1 is equal to the set of vectors containing the vector 1, 2 and the vector 3, 3. Right? You can see that these vectors are not parallel, so they are a basis for two-dimensional space. Basis 2, beta 2, is equal to the 2 vectors 2, 1 and negative 1, 1. These 2 vectors also are not linearly independent. They're not parallel. Therefore, they also span two-dimensional space. So problem number 1, part 1 of 10, says V is equal to the target vector 4, 5. Find the coordinates of V relative to beta 1 and the coordinates of V relative to beta 2. Okay, so let's set up such a problem. So C1 times 1, 2, right? That's a 2, and plus C2 times 3, 3 equals the target vector 4, 5. Okay, so here's our target vector 4, 5. So, to solve this problem, as usual, we go to a linear system. We go to the augmented matrix, which is 1, 2, 3, 3, 4, 5. Okay? Well, it's pretty clear. I don't even need to use a linear system here, actually. I don't even need to use an augmented matrix, because I can see that 1C1 plus 1C2 is going to carry us to the vector 4, 5. Right, it'll save us a little bit of trouble. Right, can you see that? If I let C1 be equal to 1, and I let C2 be equal to 1, then 1 plus 3 equals 4, and 2 plus 3 equals 5. Great. Therefore, I'll put this on the side here, up here, right? So the coordinates of 4, 5 relative to beta 1 is equal to 1, 1. Okay, let's see what 4, 5 is, the target vector 4, 5, relative to beta 2. Can we see that easily also? Let's see. If we have one of these, no, if we have 2 of these and 1 of those, we'll get to 4, and 2 of these and 1 of those, no, we don't get to 5, do we? Rats, okay? How about, I don't know, let's just use a linear system and solve. Let's use an augmented matrix and solve it. So we have the augmented matrix 2, 1, negative 1, 1, 4, 5. And let's reduce this linear system, see what happens. So if I say, all right, how about row 1 minus 2 row 2s? right? So what do I have? 0. Negative 1 minus 2 of these guys is negative 3. All right? And 4 minus 2 of these people is 4 minus 10 is negative 7, right? Negative 6. Oh, that's nice. Much nicer. All right? 4 minus 10, yeah, it's negative 6. Now, we have 1 here and a 1 there, okay? And 5 here, okay? So how about, let's say, we divide row 1 by negative 3. If I do that, I have a 1 here and then a 2, okay? And then I take row 2 minus row 1, and I have 1, 0, 3. If I interchange row 1 and row 2, I have 1, 0, 0, 1, and 3, 2. Okay, therefore, if I take 3 of these and 2 of those, can I get to 4, 5? Yes, because 3 2s is 6, minus 2 1s is certainly 4, okay? And then if I take 3 of these and 2 of those, do I get to 5? Yes, I do. So 3 and 2. All right, so you see the coordinates are different depending upon the basis that we use. The coordinates of 4, 5 relative to basis 1 is the vector 1, 1, and the coordinates of 4, 5 relative to beta 2 are 3, 2. Different coordinates, right? Relative to the standard basis, of course, the coordinates of 4, 5 are just 4, 5. I'll write that there just for the fun of it. The coordinates of 4, 5 relative to the standard basis, you know what I mean, E1 and E2, is just equal to the vector 4, 5. Okay, so the coordinates vary depending upon the basis that you use. Okay, the next part is a little bit more work, right? Part 2. So this was part 1. So the problem of part 1 is to find the transition matrix. Okay, we're going to call that I, going from beta 1 to beta 2. Now, what is this? This is going to be a matrix. And what is this matrix going to do? What this matrix is going to do is going to say, hey man, if I have the coordinates of a location 4, 5 relative to beta 1, can I find a machine that gives me the coordinates of 4, 5 relative to beta 2? And the answer is yes. And this is a machine that's going to do that. Now, to produce this machine, here are the following requirements. What we need to do is take, I'm going to label these vectors in these two bases. Here's V1, V2, and let's call this W1 and W2. Okay? So the machine, the matrix that's going to enable us to do that is to take V1 and write the coordinates of V1 relative to beta 2. Then we're going to take the coordinates of V2, the second vector of the first basis, and write that also with respect to the coordinates beta 2. Okay? That's how we're going to build the machine. And then once we have this machine, this matrix, we can take this matrix, multiply the coordinates of 4, 5 relative to beta 1 to produce this 3, 2. Okay, let's do this carefully. So we want V1. Well, V1 is 1, 2. We want to write that with respect to beta 2. All right? I'm going to keep this over here and try to do some work on the side here. So I'll do some work on scrap paper, right? So I want to find 1, 2, the vector 1, 2, with respect, I want to find the coordinates of vector 1, 2 relative to beta 2. That means I need to find C1 times 2, 1 plus C2 times negative 1, 1, and I want that to equal 1, 2. All right, so let's go to the augmented matrix here, all right? So we have 2, negative 1, 1, 1, equals 1, 2. All right? So once again, we reduce this. Take 2 row 2's away from row 1. Okay, I was just thinking for a second. All right, 2 row 2's away from row 1. That's a 0. This is a negative 3. And 1 minus 2 of these is a negative 3. Okay? Then I will divide row 1 by negative 3. We'll test this out to make sure that we got it right. And then we have row 2 minus row 1. This gives me a 0 here, and it gives me a 1 there. All right? So if I interchange this, what do we have? We have 1, 0, 1, and 0, 1, 1. Does that mean that if C1 is equal to 1 and C2 is equal to 1, that will carry us to 1, 2? I believe that's true, because 1 times 2, and then 1 times negative 1 is 1. And then we have 1 plus 1 is 2. Great. So the first vector of our machine matrix has been found. It's 1, 1. Okay? So we have 1, 1 here. Now, what we need to do is get V2, which is 3, 3's coordinates with respect to beta 2. So we want to solve the vector equation, C1 times 2, 1 plus C2 times negative 1, 1 equals 3, 3. Okay? All right, well, let's do the same thing. 2, negative 1, 1, 1, 3, 3. Okay, and we'll row reduce this. Okay, so I take row 2 minus 2 row 1, 0, negative 3. 3 minus 2 of these is also negative 3. Then I have 1, 1, 3, okay? Now I'll divide row 1 by negative 3. That gives me a 0, 1, 1. And then row 2 minus row 1. If I take row 2 minus row 1, I get a 0 here, and I get a 2 here. If I interchange these two, I have 1, 0, 2, and 0, 1, 1. That means that the coordinates of V2, this V2 here, the coordinates of V2 relative to basis 2 are 2, 1. Those are the coordinates. We'll test that out and make sure that that's true, right? So if I take 2 of these guys and then 1 of the vector negative 1, 1, do I get to 3, 3? Well, certainly 4 minus 1 is 3, and 2 plus 1 is 3. Yay! So I have produced a machine, which is a matrix, okay, that's going to carry the coordinates of 4, 5 relative to basis 1 to the coordinates of basis 2. And let's see if that works. Okay, so this is our, we call this a transition matrix, by the way. All right, so this transition matrix, if I take this transition matrix and multiply it by the coordinates of 4, 5 relative to beta 1, which are 1, 1, do I get the coordinates of 4, 5 relative to beta 2? I certainly hope so. Using the dot product, we have 1 plus 2 is 3, and then we have 1 plus 1 is 2. Absolutely. We get the coordinates of 1. So, you know, I like to say if this is a bus system, right? So if this is a bus system, with the old bus system, we used to take bus 1, 1 stop, and bus 2, 2 stops, and that brought us to the location, the absolute location 4, 5, right? But then a new bus system comes to town, which are, you know, the buses go in the direction of these two vectors, right? 2, 1 and negative 1, 1. Well, if I take, you know, so the idea was that if I take bus W1, you know, that's the new bus, right? 3 stops, and W2, 2 stops, I'll get to the absolute location 4, 5. Well, this is a transition matrix, which will give us the coordinates of any location, not just 4 or 5, any location that we want to go. It'll give us the coordinates relative to the second bus system. Let's check that out, okay? So we have this transition matrix, or I'll put that on the side. I from beta 1 to beta 2 is equal to the matrix 1, 2, 1, 1, okay? So let's get another location other than 4 or 5. Let's pick an easy location. How about the location, let's see, how about the location, instead of 4 or 5, if we took the old buses, 1 stop here and 2 stops there, what would that do? That would take us to the absolute location 7, and 1 plus 2 of these, so 2 plus 6 will go to 8. So 7, 8 is now the absolute location. And the coordinates of 7, 8 relative to the old basis were 1 and 2, right? We took this 1 stop and this 2 stops, right? And that took us to 7, 8. 1 stop on this vector, 2 stops on that vector, takes us to 7, 8. Now, if I want to find the coordinates of 7, 8 relative to the new bus system, okay, all right, let's see. We want 7, 8, that's going to be our absolute location, but we want the coordinates relative to the new bus system. So I take the matrix 1, 2, 1, 1 times the vector 1, 2, and let's see what that gives us. It gives us, once we do the dot product thing, we have 1 plus 4 is 5, so we need 5 stops along the first bus, and then we say 1 plus 2 is 3, and 3 stops on the second bus. That ought to take us to the absolute location 7, 8. Let's see if that works. In other words, if we say 5 times 2, 1, plus 3 times negative 1, 1, will that take us to 7, 8? 5 times 2 is 10, minus 3 is 7, so far so good. 5 times 1 is 5, plus 3 is 8. Absolutely, right? So the coordinates are 5, 3. So you see, this is quite convenient. If we want to change bases from base 1 to base 2, one bus system to another bus system, and in computer applications, there's a wide variety of problems we can solve in this way, right? We can get the coordinates relative to another basis by this machine. Okay, so that's part 2. So part 2, the solution to part 2 is right here. Okay, part 3. What does part 3 say? Part 3 says that we want to find the transition matrix from beta 2 back to beta 1. Let's see if they want to go back to the old bus system and say, hey, to get to the absolute location 7, 8, if we know 5, 3 are the coordinates relative to the new bus system, well, can we get the coordinates, can we recoup the coordinates 1, 2? Well, part 3 and part 4 dovetail, because what's being said here is that if we find the inverse of this matrix, part 3 and 4, okay, part 3 and 4 says if I find the inverse of this matrix, I beta 2 to beta 1 is going to be equal to the inverse of the matrix, the transition matrix, from beta 1 to beta 2. So all I have to do is find the inverse of the matrix we found in part 2. So let's go ahead and do that. So the inverse of that matrix is going to be what? We interchange the A and the D. Well, nothing happens there, right? We negate the off-diagonal elements, and then we divide by the determinant. Well, the determinant is negative 1, so if we divide each one of these by negative 1, I obtain negative 1, positive 2, positive 1, negative 1. And that's the inverse of that matrix. Let's just check that out to make sure. So 1, 2, 1, 1 times negative 1, 2, 1, negative 1. Does that produce the identity matrix when we do the dot product thing? Let's see. We have negative 1 plus 2 is indeed 1. 2 minus 2 is 0. and then we have 1 and 1 cancel each other out, and then we have 2 minus 1 is 1. Yep. Okay, so this is indeed the inverse matrix. So let's test this out. Let's take the location, the coordinates of 7, 8 relative to the second bus system, the second basis, which is 5, 3, multiply by this matrix, and hopefully we'll get the vector 1, 2. All right, so let's make sure that happens. So we have negative 1, 2, 1, negative 1, and then we multiply that by 5, 3. We multiply that into the vector 5, 3, and let's see what we get. We have negative 5 plus 6 is 1. So far, so good. And then we have 5 minus 3, which is 2. Yep. So this inverse matrix carries coordinates relative to the new basis back to the old basis. So if they decide to go back to the old bus system, then you say, well, I used to take bus 1, this bus, 2, 1, the 2, 1 bus, 5 stops, and I used to take the bus 2, negative 1, 1, 3 stops, and I got to the absolute location 7, 8, right? Well, no problem. I want to go back to the old bus system, so I just multiply by this inverse matrix, which also gives us step 5. So problem 11 gives us a set of a whole bunch of vectors. So here's set S, and we have 5 vectors here. Now, we have 5 vectors in 3-dimensional space. Obviously, this is too many vectors, so it cannot be a basis, all right? Well, so what we would like to do is find a basis for the span of all of these vectors. This is a procedure called the trim procedure. And what we do is we row reduce this matrix, and then we look for the location of the leading ones. The location of the leading ones will give us precisely the vectors that we need to span the space the span of S. All right? So let's create a matrix out of this. So negative 1, 0, negative 1, negative 1, negative 1. All right? And we're going to row reduce this. 1, 2, 3, 5, 3. 1, 1, 2, 3, 3. Okay. Well, row reducing this matrix, I'll try to do this accurately. We take row 1 added to row 2. That gives me a 0 here, a 2 here, a 2 here, a 4 here, and a 2 here. Okay, fine. How about we divide row 2 by 2? Okay, so that gives us 1, 1, 2, 1. Perfect. Now we'll add row 1 to row 3. 0, 1, 1, 2, 2. Okay? Now how about we subtract row 2 from row 3? Right? Row 3 minus row 2. 0, 0, 0, 1. Okay, this matrix is now in reduced row echelon form. Well, let me multiply row 2 by negative 1. There we go. And all of these negatives disappear. And then now this matrix is in reduced row echelon form. Notice that the leading ones occur in column 1, column 2, and column 5. All right? Now what that means is that if we call these vectors v1, v2, v3, v4, and v5, we find that to articulate the span of these vectors over the real numbers, we don't need vectors 3 and 4. All we need are vectors 1, 2, and 5, and that does the job. Notice that these vectors are not necessarily the span of these vectors, although I believe they are because I think they're linearly independent, right? However, we can write the span of this original set of 5 vectors by choosing v1, v2, and v5. In other words, the span of S over the real numbers, that just means, real coefficients, recall, that just means coefficients times each one of these vectors is equal to the span over R of vectors v1, v2, and v5. It's called a trim procedure. Okay.